Hello and welcome back. Don't forget to smash like and subscribe. It's getting late, but I noticed I gained a couple of subscribers and I thought I'd do you all a favor and make a new video. So I really hope you enjoy it. So I was going to pick up where we left off on the last one, but I lost my progress here. I wanted to have a full chart of all the questions we went through. So what we'll do is we'll solve another one of these Boolean algebra equations. But this time I really want to demonstrate the purpose of why we even want to do that in the first place. So let's just get into it. So you can see we have our equation here, and what I want to do is demonstrate what this actually looks like in terms of the circuit and the connections and components required to make this happen. So you can see that our output is dependent on these two separate terms, separated by the addition, which we also know by this point is the OR function. So we know our output will ultimately come out of one singular OR gate. I'm going to call the output X. And these two inputs will represent these two terms. So I'm just going to start with the term on the right, because this term has less going on, and we can just fill it in easy at the top here. And then afterwards, we'll do this one on the left. So you can see C bar A, D. These are all being multiplied or ANDed with each other. So essentially, the output of this term is a function of AND. So that means somewhere over here, we're going to need an AND gate feeding here. And this AND gate is actually going to have three different inputs. And keep in mind, a 3-input AND gate is just a combination of two 2-input AND gates. So for the sake of ease, I'm going to go in alphabetical order here. I'll set up all of our variables on the left. These could be push buttons. They could be light switches. Who knows really. But we do know that this AND term has an A directly. It also has a D. It also has a C bar. And as we've talked about previously, a bar is an inversion, i.e. a NOT gate. So this AND gate here represents this term. So in order for this AND gate to actually output a 1, all of its inputs would have to equal 1. That's what an AND gate is. So for this AND gate to output a 1, A would need to equal 1, D would need to equal 1, and C would have to equal 0, because C gets inverted, as per this bar. Now we're going to look at this term on the left, and I'm changing colors to blue for this one, just to keep life easy. So the first thing I'd like to note about this term on the left is the big overbars on top. Now, as we've covered before, if you have variables underneath an overbar, they will be in a single group underneath that overbar. In this case, 2 overbars. So what does that mean? The overbar is the NOT function. And so these 2 NOT functions, these 2 inversions, will apply to this entire B bar D B term. So to put it simply, B bar D B gets inverted as a whole 2 times. So I can draw this as 2 NOT gates. And these 2 NOT gates will apply to the B bar D B. And this term is another AND gate, a 3-input AND gate similar to the term on the right. So this AND gate has 2 B inputs. It has B. It also has B bar. The last input this AND gate has is a D. And so, if you were to purchase pre-made logic gates or transistors and resistors or what have you, or if you were doing software programming and you created this physical circuit or code, you would find that this circuit down here is representative of this function on the top. X would be equal to 1 if either blue or red became true. And you can see there's quite a few logic gates and connections required to make this happen. So what we're going to do next is we're going to first simplify this Boolean expression and then make the circuit again and compare the two side by side. So to simplify this circuit, I'm going to start with the term on the left. And remember this B bar DB is one group here in a bracket. These 2 NOT functions apply to the bracket as a whole. And we're going to start off with the 2 overbars up here. And this is fairly straightforward. So imagine if B bar DB was equal to 1. The first bar would invert the function and turn it into a 0. And the second bar would turn it back into a 1. So basically the idea is if you invert something twice in a Boolean system with only 2 possible states, it's as if you've done nothing at all. And that's like me saying, I don't not want $1 million and a cool hat. That really just means I do want a cool hat and $1 million. So essentially, this term can be simplified to B bar DB, and that's the law of double negation, I believe. And so we can see this can actually be simplified even further. Because if you watched the last video, or if you know your stuff, you'll see here we have B bar multiplied by D multiplied by B. Just ignore the D. So pretend we have X bar multiplied by X. What is that going to do? Well, in a digital world where you have 2 opposites, one of them is going to be a 1 and one of them is going to be a 0. When you multiply them together, you will get 0 every time. And so it really doesn't matter what this D actually is, because it's being multiplied by a 1 and a 0. So it's being multiplied by a 0. So this whole term is equal to 0. And we could delete this entire left side of the equation just like that. All of this does not have any effect whatsoever. Now, the term on the right, basically cannot be simplified anymore. And what this means is our entire equation is equal to nothing but c bar AD. So if we wanted to do what we did at the beginning and draw out what this actually looks like, you can see first of all, we don't even need the variable b. It has no effect on the final outcome. We only need to use 3 variables, a, c, and d. So that's already saving your resources. And we can simply connect these 3 variables through a AND gate, a 3-input AND gate, keep in mind. And all you need is a singular inverter or a NOT gate. And that's for our C bar. And this is our X, our output. So what we're saying is, this circuit that you see right here, consisting of 2 logic gates, is the exact same in terms of functionality as this entire circuit here, which has 1, 2, 3, 4, 5, 6, 7 logic gates. You've eliminated one variable. You don't need B anymore. You've eliminated everything in blue. You've also eliminated this last OR gate because you don't need that anymore. Because whatever output this is, 0 or 1, would be the same on the other side of this OR gate. So there's no point. So that not only saves you components and connections, but it can also potentially save speed. If you're talking about a big scale, like if you had many of these things, they do have some sort of time limit to do a process. So in a small circuit like this, you might not notice, but a complex system, if you can cut down from like 7 million to 2 million, for example, logic gates, instead of 7 to 2, you can see how you would be saving a lot of speed, power. It's simpler, it's cheaper, has the exact same output for the same given inputs. So, now that we've concluded that our answer is C bar AD, let's just check in our quiz here and select this answer and see that it gives us the green, and we know green is good. So that's all the time we're going to have for this one. Smash like, subscribe. Yeah, thank you.